Alien dictionary, this is a premium hard problem. So we can solve it using a topological sort and also using a BFS Ingegree solution. So in the previous video, I have discussed how to solve it using topological sort. So in this video, I'll be discussing how to solve it using the Ingegree BFS solution. So let's see the problem once. There is a new alien language that uses the English alphabet. However, the order of the letters is unknown to you. In our English language dictionary, we use the order like A, B, C, D to Z, means B comes after A, C comes after B, and so on. But in this dictionary, they can follow any other rules. You are given a list of strings, words from the alien languages dictionary. Now it is claimed that the strings in words are sorted lexicographically by the rules of this new language. So if these are the words we are given, then these are sorted based on their new language rule. If this claim is incorrect and the given arrangement of strings in orders cannot correspond to any order of letters, return empty string. That means basically if we have any invalid input, we can return empty string. Otherwise, return a string of the unique letters in the new alien language sorted in lexicographical increasing order by the new language's rules. If there are multiple solutions, return any of them. So, if we consider this string, these words, there can be any rules. The output is WERTF. That means in their language, W comes before E, E comes before R comes before T comes before F. Right? This is some kind of order that we have to find out from these words. Let's take few simple example like Z and X. So that means this is the dictionary. Z comes before X, right? So the order is just one order, Z and X, Z then X. If we see this words list, this is Z comes Z then X then Z means Z comes before X, then again X comes before Z. This is not possible, right? There is a cycle. So this is an invalid input, so we have to return empty string in this case. So consider this example given. So these are the words list in the dictionary, in the alien dictionary, and this words comes in this order. So first we have to create the adjacency list. How do we create the adjacency list? We will compare the words pairwise and we'll look for the first non-matching character. Like here, W and R matches, but T comes before F. So in the adjacency list, we'll add one H like T to F, right? T comes before F. Compare this to W comes before E. Compare this to R comes before T. Just one thing is when there is a mismatch like here see R comes before T, right? We don't need to check for the rest of the characters. Rest of the character can be in any order, that's not important here. So consider this two, E comes before R. So this way we'll be creating the adjacency list so that we can use it in our BFS solution. Next talk about Ingegree. What is Ingegree? Like just a quick brief. So consider this graph. Here A and C doesn't have any incoming edge. So the Ingegree of A and C will be 0. B has 2 incoming edge, so Ingegree of B will be 2. D has 2 incoming edge, Ingegree of D is 2. E has 1 edge, Ingegree of E is 1. So we will use this Integrees for our algorithm. How we will use this? So the algorithm we are using, that is called Kahn's algorithm. So this is basically Ingegree BFS algorithm. Consider the same graph. What we'll do is we'll take the BFSQ as well, right? And we'll first take all the Ingegree 0 characters in our queue, like only A and C. Next, we'll take A and we'll add it in our output. Because A doesn't have any characters that comes before A. So A can be in our output. When we process A, we'll see all of its neighbors. A has only one neighbor, that is B. We'll get rid of this B, we'll get rid of this H and we'll decrease the integrity of B. So integrity of B can be reduced to 1 because we're just getting rid of this A to B dependency. Next, we'll consider C. C can be in our output. C doesn't have any characters that comes before C. Now we'll consider the neighbors of C, that is B and D. We'll get rid of those edges and we'll reduce the integers of B and D. Integer of B will become 0, integer of D will become 1. As soon as the integer of B has become 0, we can add it in our output. Now we'll process B. Now we can add B in our output. Why? Because B comes after A and C and both are processed. So now we can process B. So integrity of B has become 0 only after all the characters A and C has been processed. When we are processing B, we'll get rid of this H, B, D, H and will decrease the integrity of D. So integrity of D will become 0. Next, as integrity of D has become 0, we can add it in our output. Next, consider D. D has integrity 0 at this moment because all the characters that comes before D, A, B, C, all these 3 characters has been processed. Now we can process D. D now has integrity 0. So we can add it in our output. Now we'll get rid of this H, D, E and will decrease the integrity of E. That will become 0. Right? So we can add it in our queue and then E doesn't have any other neighbors. So we can process E and we can add it in our queue. So our solution will be A, C, B, D, E. Now consider, apply this solution in our input given. So these are the words in the alien dictionary. Comes in this order. So I will compare the pairs and will create this adjacency list first. Then I will also compute the integers and then I will do the BFS processing. So WRT, WRF, T comes before F. Here W comes before E. Here R comes before T. Here I comes before R. These are the adjacency list edges we found. Now we'll also process the integers. Integers of F you see only one edge from T to F. Integrity of E is also 1. Integrity of T is also 1. Integrity of R is also 1. Integrity of W is 0 because there is no word that comes before W. So first we will put W in our queue. W has E as neighbor, will reduce the integrity of E. Integrity of E will become 0. But before that we will process W, right? That can be in our output. Now integrity of E has become 0. We can put it in our queue. So and we will process all the neighbors of E. E has this E to R, this only one neighbor. So we'll reduce the integrity of R to 0. At this moment E has already been processed. It can be added to our output. Next we are adding R. So R has integrity 0 now, so I can add it in our output. We'll check for all the neighbors of R. R has only one neighbor, that is T, right? So that will decrease the integrity of T, that will become 0, and as it is 0 we can add it in our queue. Now T has integrity 0 now at this moment because we are processing. We can add T in our output. Now consider that neighbors of T. T has only one neighbor, that is F. Will decrease the integrity of F. that will become 0. We can add it in here. So at this moment, if is in degree 0, we can add it in our output. Now here you see all the nodes, all the character has been processed, and our output will be WERTF. Now how this algorithm detects cycle? Consider this input ZXA, ZB, ZX. Okay, so compare Z and X. Z comes before X comes before A comes before Z, B comes before X. These are the adjacency list. Let's create the graph just for our understanding visually. I am just creating the graph. Z to X, X to A, again A to Z. There is a cycle. This is a cycle. Then B to X. But there is a cycle. How our algorithm will detect it? These are the integrees. X has two integrees, one from Z, one from B. Initially, A has one integree, Z has one integree, B has 0 integree. So first we'll be processing B. So B will be in our queue. Now what is like B's neighbor is X. So we'll decrease the integree of X. It will become 1. Right? So we process B, B is in our output. But you see, already you have processed B. These are the left out nodes, left out characters. Is there any in degree 0 nodes? No, right? So we cannot put any characters in our queue at this moment. Our algorithm will end here, right? So then in that case, how do we decide is there any cycle? The logic is, if you see the length of the output is less than length of all the characters, right? If length of the output is less than length of all the characters, there are 4 characters, right? So in that case, we can say there is a cycle. But how? Intuitively, we will understand this. We'll see in the next slide. Consider these graphs. This is the first graph. Integrity of this node is 0. When I will process this, I will add it in my output. I will get rid of this edge. Integrity of this will become 0 then. We can process this. Similarly, after that, we can get rid of this 2 edges and we can process this node. This is fine. Next, consider this one. This to have integrity 0. We'll process this layers. Consider this is one BFS layer, one level, right? So this one will be processed first. We'll get rid of this edge. The degree of this one will become 1. We'll process this one. We'll get rid of this edge. In degree of this one will become 0. At this moment, after the second level, we can process this node. Here, there is a cycle. How? This node has integrity 1. This node has integrity 1. Right? So, we cannot start our BFS processing because there is no integrity 0 nodes here. Right? So, our output will be empty. But the characters, there are 2 characters. So, we can return that yes, there is a cycle. Next one. Consider this node, this character. This has integrity 0. We'll get rid of, we'll process this edge. We'll add it in our output. We'll get rid of this edge. This integrity of this one will become 1 for this one. Because this one we are deducting, but this one we will have. So at this moment also again, there is no integrity 0 add in the next level. So we cannot process these 2 characters. So character output will be of length 1, but there are 3 characters. So we'll be able to detect the cycle. Next one is the same. In the first we'll be processing this one. We'll get rid of this one. The integrity of this will become 1 from this edge. So down the line, from any node, if there is any edge coming back, there is a back edge to any node, right? So that will, if there is a back edge, then this integrity of this node cannot become 0. So at any edge, if we see this kind of bottling is happening, means we have to stop our processing from that node. So if in that case, our output length will be less, right? Will not be able to process the rest of the nodes. So in this case, our will be able to detect one cycle. What is the time complexity of this algorithm? Consider there are n words, k is max word length. So if there are n words and k max length, so approximately there will be nk characters total. I'm not talking about the unique characters but total. So building the adjacency list, we have to go through all the characters. So that will be order of n multiplied by k, that is close to order of s. What is s? Sum of length of all words, right? So that will be our building the adjacency list complexity. C is total unique characters. So in the earlier problem we saw only 4 unique characters we had. So the total unique characters. E is the edges, number of adjacency relations we are forming from the rules, from the words given, right? So if C and E is this, so BFS Ingegree solution will have complexity order of C plus C. This many times for this many nodes we are calculating doing the DFS, and these are the ages. So it will be order of C plus C, and overall complexity will be order of S plus C plus P E. Not sure which one will dominate what. Space complexity. For adjacency list, order of C plus C, because there are unique C characters and depends on the number of ages we are formulating. BFS Q for Ingegree solution. The Q will have order of C, the number of unique character, that many that will be the Q length at max. So that will be order of C. So in total it will be order of C plus E. So first we'll be creating a adjacency list. So adjacency list, it will be a default text of list, because for each character I need to see what all characters comes after this character. So we need a default text of list. What we need a Ingegree's map as well. That will be a dictionary, or it can be a default text of int, because it will store for each character the in degrees of that character, like it comes after how many character. Next, I'll be processing the words given. We'll compare each pair and we'll compute this adjacency list and the Ingegree's list. For I in range length of words -1, because I am taking a pair, word 1, word 2 will be words I and words I plus 1. Then for j in range minimum of length of word 1 and length of word 2, I'll just check if the character at jth position matches or not. If word 1 of j not equals to word 2 of j, means we are getting a mismatch, then we have to update our adjacency list, right? Adjacency list of word 1 j dot append word 2 of j, means word 2j comes after word 1j. Now also you have to update the Ingegrees. Ingegrees of word 2j will be +1, because from word 1j to word 2j we have an h, so word 2j comes after word 1j. So Ingegrees of word 2j has to be incremented. Now that's it. And also I forgot, I have to take care of the character set. So this is a set I am keeping. So here I'll be adding all my characters. So let's add both the character, word 1 of j, word 2 of j, because both are different. Otherwise, characters dot add word 1 of j, they both are same, so I can add 1. But whenever we are seeing a mismatch, we are populating these things and then we have to break that, because the rest of the characters doesn't matter, they don't create any rules. So the first mismatch only will create one rule. Fine. Next, what we have to do now, if let's consider the apple and app scenario. If apple comes before app, till app everything is matching, but apple should not come before app, right? So that scenario, how we will test, if j equals to length of minimum of length of word 1, length of word 2 minus 1, and word 1 j equals to word 2 till j, and length of word 1 greater than length of word 2, then return empty. This is an invalid input. Now I have to update the character list as well, character set as well, because let's say apple and app, so we process till app, right? App comes, let's say the valid scenario, app comes before apple, right? We updated, we consider till app, but the l and e needs to be added to the character set, right? So we'll update word 1 from j, and also word 2 from j, and also, and we are done with processing my character list. We are done processing the Integrees and adjacency list and the character set. Next we have to do the actual BFS call with Integrees. Now we have populated all the characters, but Integrees are not updated here for characters that have Integrees 0, right? We could not find one age for those, right? So let's do that. Integree zeros will be what? Characters dot difference integree dot keys. So integree dot keys returns all the characters that have integree, at least some integree, like greater than 0, right? And characters contains all the characters. So if we take the difference, that will give me the integrees zeros. Uh, that will give me the characters that have integrees 0. Done. Now we have to create one queue. Let's create it with the integree zeros node. So integrity 0 nodes are not coming after any character, so we can directly add it to our output. So this is, let's say this is my output, and I'll process my queue, process this till we have some element in my queue. I'll just do queue dot pop left, right? So that will give me a character at each time. So this character, whenever I am popping from the queue, that means this character has integrity 0, right? So at this moment we can add it to my output, right? Done. Now we have to process all the neighbors of this character. For neighbor in adjacency list of this character, right? I will do, what I will do is, let's say from W to R we have some age, assume. So when, if W has integrity 0, I process that, I added in my output. Then W to R we have some age, so I am processing R, right? Before processing R, I can remove the age from W to R. If I remove that, then R's integrity will be reduced, right? R's integrity will be reduced to 0. Integrity of, this is integrity or integrees, what I have taken, integrees, sorry, yeah, integrees of neighbor minus equals to 1. We are reducing. Now if n degrees of neighbor equals to 0, then we can add it in my queue. That's it. We are done. So every time we are adding, if it is becoming in degree 0, I am adding it to queue, I am processing, and I am outputting it in my output list. That's it. Now how about detecting the cycles? If length of output is less than length of characters, that means we haven't processed any, we have not processed few characters, and that means there is a cycle. We discussed how why it is. So we can return empty list, right? And otherwise we'll return a string from this output list. Now let's run this. Okay, everything passes. Next, let's submit this. Wow, this paid 100%.